In this video, we're going to build on the transformational graphing from the previous video that focused on translations and reflections using vertex form, as well as all of the different combination of transformations that can occur. So if you haven't watched the previous video, you would definitely want to write down this part of the notes, as well as the review section of what each one of them does. So you'd want to pause and write this part down, and then pause and write this part down. And then you would want to refer back to the previous video on transformational graphing. But in this video, we're going to look specifically at examples of dilation, as well as mixed transformations. All right, so the first example here, first couple examples don't have a transformation in terms of their translation, but they do have a dilation. So all of these problems can be broken down into just 3 steps. They follow the order of operations that I call Gelmdas, grouping symbol, in this case the absolute value, exponent, which is a cube, and sometimes you'll have a logarithm for another chapter. So in that Gelmdas example, G through L is identify the parent function, which in the first problem is the absolute value. So what you're going to do to start the problem out is you'll simply graph those values, which start at the origin, always 0, 0. The absolute value of -1 is 1. The absolute value of 1 is 1. The absolute value of -2 is 2. The absolute value of +2 is 2. Then what you're going to do is look for a multiplier. Remember, in Gelmdas, after I have identified the grouping symbol, exponent, or logarithm, I now am moving to multiply or divide, which in this world, in this case, what I have is I have a multiplier, right? Notice it's on the outside of the grouping symbol, so multipliers affect the output. It's an important thing to remember. So what I'm going to do is I'm going to multiply all of my output values on the graph by 2. So 0 times 2 is 0. Remember the output, another way of explaining the output is it's like the height of the graph. So this 1 going this way doesn't change, but the height of 1 will now be 2. And this height here, again, the -1 doesn't change, but the height of 1 will now be 1 times 2, or 2. And the height here that's already 2 will be 4, and so will this. Again, some students need to go back and erase the other ones. I like to leave them there so people can see it when they see the notes later. Then the last step is always to check for a translation, which in this case, there's nothing inside the grouping symbol, so H is 0. There's nothing outside the grouping symbol, so K is 0. So I will simply graph my graph, and it's important here because you might mistakenly draw this in the wrong shape. It's important to remember that this is a V, right? So when I draw this, I want to make sure that it's V-shaped and not U-shaped, because if I make it U-shaped, I actually accidentally drew the quadratic, and this one is clearly the absolute value. All right, let's take a look at the next one, which is cubic. So one of the things you'll notice when you have a problem like this is they do not put a parentheses unless you have a B value. If it is an A value, they won't put a parentheses here. So as a student, if you want to put the parentheses, it would go here. Otherwise, it would be a B because it would include it inside. Just keep that in mind. All right, so we're going to graph the parent function for the cube. And when you have a cube graph, you have to make sure that you graph by 2s to fit all the key points in. 0, 0, of course, and 1, 1, of course. Those are the same for all parent functions. Then I have -1, -1, because if you take -1 and cube it, you get -1. And then I have -2, -8, and I have 2, 8. All right, so then we'll take a look at the multiplier, which in this case, this multiplier here, I'm multiplying the function by 1/2. So again, it's a multiplier. It's outside of the parentheses. It's going to affect the output values. So let's take a look at what that looks like. Again, this one always stays here. That's convenient. So then this height, that's 1, will now be 1/2, but I don't change this value here. This one will be -1 instead of being -1 in the height, it's now -1/2. This one that's 8 will now be 4. Don't change the input of 2, and the input of -2 will now map to -4. All right, and then let's take a look and see if we have a vertex. Again, there's nothing inside this parentheses, so H is 0. There's nothing outside the parentheses, so K is 0. So I will graph the cube and the cube has been made smaller. So what is the proper way to say that? Because we don't want to just say whatever words we want. Math is a very precise subject. So when it has been made larger, like in this case, we multiply by 2, the graph has gotten larger. That is called a stretch. But in this case, it has been made smaller going towards this axis, and that is called a compression. So let's take a look, and specifically, those are both vertical. So translation, both of them had none. Reflection, neither one of them had a reflection. However, the dilation, and think about that word, the word dilation is like when you go to the optometrist and they dilate your pupils. Unfortunately, in that case, they just get bigger, but dilation can also mean to get smaller. So this one was dilated with a stretch vertically by 2. You could also say vertical stretch of 2. This one was compressed vertically by 1/2. All right, let's take a look at 2 more examples where I did throw in a little bit of a vertex change as well. So for the first one, we see the square root. So step 1 is to draw the parent function of the square root, which is 0, 0. The square root of 1 is 1. The square root of 2, I don't know. The square root of 3, I don't know. But the square root of 4 is 2. And again, the next one would be 9, 3, which would be over here, which is irrelevant. We never have any negatives to start with, that is, and we never have any negatives over here to start with. All right, so then the next thing is, well, what do I have? Well, this is inside. So technically, this would have to be, it's technically factored out every time. So technically, we would factor that out, showing us what the b value would be. So the b value is 4. It is a divider, because to factor that out, you have to GCF factor it by dividing it. And dividers are on the inside, affecting the input values. So let's take a look at what that would do. If I take a look at what happens, again, 0, 0 does not change, but this input value of 1 is now 1/2, but the height is the same. So instead of being 1, we're now at 1/2. Still outputting 1 though. And here, our input value is 4, but it's dividing it by 4. So that should have been at 1/4. Sorry, my brain was thinking about the previous example. We're dividing, in this case, by 4. So instead of being at 1, we're going to be at 1/4. It still maintained the height of 1. But this one's at 4, right? It's at 4. We're dividing that by 4. So it'll go from 4 all the way back down to 1, but it will still have a height of 2. So think about this dot. It basically just got reduced by dividing it by 4. So if there are 4 boxes here, if I divide that by 4, I am at 1 box. And if here I have 1 box, I'm at 1/4 of a box. Okay, this one does have a vertex change as well. There is no H you can see, but there is a vertex change to move all of the points up by 2. So once you're at this step, you're just counting boxes. So the vertex, go up 1, 2, boom. This point, go up 1, 2, boom. This one's also going to go up 1, 2, and that will be where my final graph is. My final graph will be here, looking like the square root. That one had all 3, and we'll go over what happened when we finish the next one. All right, so this one is a square, okay? So we have to remember the values for square using our parent function. And that would be, again, we always have that 0, 0, and we always have 1, 1. So those are easy, 0, 0, and 1, 1. But we're squaring, so -1 would also be 1, and 2 would now be 4. And -2 would be at +4 as well, just squaring those values. So I took care of the parent function. So now we have a divider. Again, it's on the inside. Technically, you're factoring this out. You're dividing by -1/2. So this one's also going to have a reflection. So that happens simultaneously, though when we write it out, we write it as 2 different things. So I'll explain how that works. We're going to be dividing, okay, the inputs, right? Dividing the inputs by -1/2. So let's take a look at what that does. 0, 0 is a give me. It's always nice to start with something that's easy. So this point is going to be divided by 1/2, which actually makes it bigger, because if you take 1 and divide that by 1/2, the 1/2 will reciprocate and then multiply by that reciprocal, and so you actually end up with 2. So this value will go to 2, but since it's negative, it'll be negative 2, but the height doesn't change. In this point, right, if I change this value right here to a 2, I would still reciprocate this, and now it would be 2 times 2. So this will now be 4, but it's negative, so it's negative 4 over there. Same thing's going to happen to the negative values, right? This negative value would become a 2, and then negative and negative, it would be positive. This negative value would become a 4, but then negative and negative makes it positive 4. So the interesting thing about a symmetric graph like a parabola or an absolute value is that when we reflect over the y-axis, which you just saw, it doesn't actually change the shape of the graph. So you really have to look here to see that it's happening, especially if a question on an assessment were not to graph it, but to just tell me what happened. You would really have to look at that negative, because on the graph you wouldn't particularly see it. All right, so let's finish this problem up by looking at the vertex. Again, there is no h. The reason I know that is there's no plus or minus in here, so we have a 0 here. And then the negative 3 will be our k value. So this is the nice kind of relaxing step at the end of the problem. I take all of these green dots and just move them down 3. That's a pretty easy process compared to having to do all the other things. I like to do them symmetrically at the same time to make sure I get them in the same spot by counting. Again, if that's too busy for you, based on the student, you could go ahead if you wanted to and erase some of them. Please keep in mind that when you graph this by hand, your teacher is going to want to see all of these dots to see that you understood the process. If you just draw a graph on the graph, they're going to think that you just got that from a calculator or a graphing program. And please keep in mind that if you were to go to Desmos or use a graphing utility like a TI or a Casio, you could just type this in and that would be the answer. So without these dots, there's no way to hold you accountable. And those dots are, in my opinion, more important than the end product. Obviously, the end product is important, but seeing that process is extremely important. All right, let's review what each of these problems did. So this one had a translation up 2. This one had a translation down 3. This had no reflection. This one had a reflection over the y-axis. Typo I'll fix there. All right. Remember, the positive value became negative and the negative value became positive, reflecting over the y-axis. The dilation here was that I compressed my graph horizontally. Now, if you're thinking about the fact that it got bigger, that's why words like bigger and smaller, they're not precise. This graph looks taller, sure, but what actually happened in this graph, and this is super important to understand, is by dividing by 4, I didn't multiply, I made the graph go in. And when the graph goes in, that is a compression, and it's happening in this case horizontally, because this is the horizontal axis. This one was stretched, and you may look at that and be like, well, that looks like it got wider. Wider is not specific, right? What happened in this graph is the dot that was here, right, it went outward, right? So did this one, and that is stretching the graph on the horizontal axis, which in this case it was stretched by 2. So forgive my little typo there. I'll go ahead and update that. So in these examples, we're going to be talking about dilation as well as mixed transformations with parent functions using the vertex formula for functions. And as things get more complicated, it's important to understand that it really just boils down to 3 steps. And those steps, if you go in order, it's not that bad. It's just following those steps and doing it at the same time. And those steps come from the order of operations, or GELMDAS. Grouping symbol and exponent being the parent function that we're going to be talking about in this chapter. Later, the L stands for logarithms, which will also be used for a parent function in a later chapter. So in this problem, we're going to be looking at the quadratic. So we'll go with the parent function for that. 0, 0 is the point for all parent functions, as well as 1, 1. From there, negative 1 squared is 1, and 2 squared is 4. And negative 2 squared is also 4. So step 1 is done. The next step is to look at the fact that I'm multiplying this 1/4. It is a multiplier. It is outside of the grouping symbol. So outside of the grouping symbol, I'm going to multiply the out output values. So what that means is I take all the output values, I multiply them by a fourth. So 0 times a fourth is still 0, but 1 times a fourth will be 1/4 of that height. Notice that the x value is still 1, but the output is now 1 times a fourth, which is a fourth. Here, our input value is still 2, and that'll give us 4, but multiply that output by a fourth, and we're now at 1. Same with this one, negative 2 squared is 4, multiplied by a fourth is 1. So from there, we're going to look at the vertex. So the vertex comes from finding h and k. H in this case is 3, and you might say, hey, that's negative. But remember, right, if you have a 3 and you put it into this equation, that 3 would go here, and it would appear negative even though the actual value is positive. So our vertex will be at 3, 0, meaning we're going to move all of our points to the right 3 and not change the up or down values. So we're going to take our vertex that's at 0, 0, we're going to go to 3, 0, place it there. Then we're going to move the points over one at a time, 3. 1, 2, 3. That point will now be there at a fourth. 1, 2, 3. That one will be there. I like to do these in symmetric pairs to make sure that we're keeping it even. You can also catch mistakes that way. This one will go 1, 2, 3 this way. This one will go 1, 2, 3 that way. Symmetric pairs. And then you draw a graph through your parent function to make sure that your teacher knows that you know what the shape is, but also to make sure that you show your teacher where you have stopped. And all of the points are important, because if you graph this original problem just like this on a calculator or a graphing utility or using Desmos, it'll just give you the answer, and without these other points, your teacher may misinterpret what you've done or think that you haven't learned all the different methods that are important to understand how this works in its totality. So the next one is the absolute value function, but what I realized is that there is a divider here. So we're going to want to go ahead and GCF factor that divider out to make sure that we know the true value of b as well as h. So we start with our grouping symbol, we take the GCF out, and then we use a parentheses, and so 2x divided by 2 is x, and then plus 2 divided by 2 would be 1. So as you can see, h is actually changed to 1 and is not actually 2 as it appeared, and the k is unchanged. Now some students after that, they'll scratch this out so they make sure they don't go back and look at the wrong values. But for right now, I'll leave it, and I'll do that when we look at the translations. So parent function in this case is the absolute value, which is 0, 0. The absolute value of negative 1 is 1. The absolute value of 1 is 1. Negative 2 is 2, and 2 would be 2. So there's your traditional absolute value v. The multiplier in this case isn't a multiplier, it is a divisor. That divisor right there divided all of these values to factor, so it will divide the, remember, it's inside the parentheses, so dividers affect the input, they're inside, as opposed to multipliers which are outside and affect the output. So I'm going to go over here, and the vertex will still be at 0, but this input value of 1 will now be divided by 2. So 1/2 of 1 is a half, but the height stays the same. At negative 1, I will have negative 1/2, height stays the same of 1, or the output value will stay that same value as of 1. So the next one, at 2, divided by 2, I get 1, but the output of 2 stays the same. Negative 2 will be negative 1, output value stays the same at 2. Then I'm going to look at the translation. The translation, and this might be a great time to kind of cross this out so I don't actually think it's 2 again. The translation is this h value, and in this case h is negative 1, because if you take negative 1 and you put it into negative h, you'll get positive 1. It's always opposite if that's too complicated once you factor b out, and k is 3. So that's going to make me graph everything to the left 1 and up 3 from the multiplier divider step, the divider step in this case. So I always like to start with the vertex. We're going to go left 1 and then up 1, 2, 3. So then that puts my vertex right where it says it should. Then I'll do these points. So left 1, up 1, 2, 3, right there. Left 1, up 1, 2, 3. right there in the middle, left 1, up 3, left 1, up 3. Then I want to go back and draw my nice V, okay, to tell my teacher that I have completed that and that I understand the shape of this is a V as opposed to a U or something else. So now what we'll do is we'll go ahead and describe what we did in those problems. So in the first problem, it was translated right 3. This one, as we just did, was translated left 1 and up 3. Neither one of them had a reflection. None of them went over the X or Y axis. However, the first one, this is very important to understand, it was compressed. So we started at this value and we compressed it down, right? So the values got compressed downward by a fourth, meaning they're 1/4 their original output values. This one was also compressed. This one was compressed downward or vertically, so you could say compressed vertically. This one was compressed inward like this. So when we compress this way, we call this horizontally, and these were compressed by a factor of 2. Okay, and actually probably a better way of saying that, that's a little, is we would want to say compressed horizontally by 1/2. The reason we want to say that is that's what has happened. It's half of its original input values. All right, so let's take a look at the next two examples. So the next one is the cube root. However, before I start doing the cube root in that case, I probably will want to take a second and factor out that negative. Yes, you need to make sure if you see any b in the problem that you factor those out. And a good way to do that, to make sure you don't accidentally miss that or make a mistake, is to, when you start an assessment of any kind, you would just want to look through the entire thing and see if you see any b's, and then just start by factoring those b's out. So we are going to divide negative x by negative 1, giving us x. We're going to divide 2 by negative 1, giving us negative 2. So then we're going to graph the parent function points for the cube root, first one being 0, 0, then always 1, 1. Notice it's in the middle here. I had to go by 2's because anything that's a power of 3, the cube or the cube root, I want to make my graph go by 2's because it involves the point 8. So negative 1 cube rooted is also negative 1, negative 8 cube rooted is negative 2, and 8 cube rooted is 2. So in this one I have both a multiplier and a divider, and since we're doing order of operations, we'll go from left to right. So in this case, my multiplier is a half. I'm going to multiply outside the grouping symbol, so output values, and that's going to make all of the heights or the output values half of what they currently are. So this one that's at 1 will be at 1/2. This one at negative 1 will be at negative 1/2. This one that's at 2 will be at 1. This one right here at negative 2 will be at negative 1. The input or x values do not change, only the y's do. Now I will look at my divider, and it will change my inputs because it's inside of the grouping symbol. So what this is going to do, again, we'll start at the vertex, that'll stay 0. It's going to change this input value. Instead of being 1, it'll be negative 1. The height has already changed, so don't make it go back up higher. It's still at a half. And then from there, this one that's at negative 1, if I divide it by negative 1, I will have 1. You can see that that just reflected over the y-axis. The one that's at 8 will be at negative 8, and the one that's at negative 8 will be at positive 8. And then the last thing to do in this case is to use my translation. Remember, that's negative 2, but h is always negative, so h in this case will be positive 2. And there is no k, so that will be 0. So now I will take all of the green dots and I will move them. It's negative 2, so there's positive 2 here, so they're all going to move to the right 2. So start with the vertex, 1, 2, right where it's supposed to be at 2, 0. This one will go forward 2, be right in here. This one will go forward 2, nice symmetric pairs there. Here I move this forward 2, and I move this to the right 2 as well. And so then from there I can draw my cube graph. You can see why it's so important to actually draw that final graph, otherwise your teacher might get lost in where you think your points are. And there you go. So the last one, interesting one, is the greatest integer function. There is a b. If you just want to factor it by putting a parenthesis here, that would be fine because there is no h to have to do the work that I had to do on the other two previous examples. So the greatest integer function is starts at 0, 0. It has 1, 1 as all do, but the greatest integer function of 2 is 2. The greatest integer function of negative 1 is 1, and negative 2 is negative 2. It just looks like a line to start off, which is a nice, easy way to start. I then have a multiplier that I need to multiply the output values. Remember, outside the grouping symbol, output values. They're going to be multiplied by 3. This one will stay at 0, but this one that's at input 1, output 1 will now be input 1, output 3. And this one at input 2, output 2 will be input 2, output 6. It's just a little over, so I don't think anybody would mind if we just put it right there. This one will be negative 2, and this one will be negative 6 a little bit down here. Now that's a great thing to think about in terms of what does this mean in the real world. Remember, the best analogy of the greatest integer function is time or age. So imagine we were on another planet where it took 3 years for us to, where the planet in 1 year would circle its sun 3 times. So 1 Earth year on this 3 times as fast orbiting planet, 1 Earth year would be 3 years on that planet. So 2 Earth years would be 6 years and such. Okay, the next thing that we're going to do, and remember, just to keep us, understanding what this looks like, this would be barbells looking like this. And this next thing is really interesting what happens. So there are current graph. The next thing that's going to happen is we're then going to take this negative 1 and divide all the inputs by negative 1. So all our inputs are going to be divided by negative 1. And what that's going to do is it's going to take this dot, this one doesn't change of course, this dot instead of being positive 1 will be negative 1. And this dot that's negative 1 will now be positive 1. This dot that's 2 on the x-axis will now be negative 2 on the x-axis, but at 6 still, and this one will be, from negative 2, it'll now be at positive 2, but still be down here. But I want you to think about what happened. This graph right here, right, it reflected over the y-axis. So this is really interesting to understand what's happened is, if I reflect this graph over the x-axis, instead of being closed open, it's now open and then closed. All of them will have that look because we have to, think about this as the line of symmetry. All of these graphs now have to change their orientation of, instead of being closed open, they're now open closed. Because remember, this literally flipped over here, right? So this flipped over, they flipped over. They have to have a symmetric look, just like this one did here, and it was clear that this was symmetric. But here, this one's a little bit trickier because of how that open circle will flip to the other side. So let's talk what happened, just kind of like a wrap up. The first one we translated right to, as you can see. This one had no translation. This must be left over from another problem. So this one had no translation. This other one here, they both reflected over the y-axis because of these negatives that were in both of them in the inside of the grouping symbol. This one was compressed vertically by a half, making it a skinnier graph, but we don't want to say skinnier or smaller. We want to say compressed vertically, so we're precise. It's important to be precise in math. And this one was stretched vertically by 3. You can see that it was at 1 and then it went to 3. All right, I hope you've enjoyed these examples. I hope that they've been informative. Feel free to watch several of them again that maybe were troubling. And when you look at your assessments, your formative assessments, make sure you go back to this because it reflects this material as well. Thank you for watching and have a nice day.